Greetings. So we are going to discuss quantum entanglement, EPR paradox, then Bell's inequalities. And these topics are of great importance because the quantum computation is just around the corner. You are probably reading about the claims and counterclaims by Google and IBM, and there is a lot of excitement about the tremendous development in technology in this field. So, there have been major advances in technology in recent times in quantum computation, and it all started with, it begins with the big development in the previous century in quantum theory, which is really an amazing theory. It's very successful. Nothing is found to violate the laws of quantum mechanics. So, it's a very powerful theory. The theory remains correct as long as you find that it is not applicable in some situation, or it doesn't give the right results, but there is no fault that has been found with quantum theory. It's a very robust theory, very successful theory. But then it also went through many challenges, and challenges by great minds, including Albert Einstein and many others, Planck, Landé, and there are a good number of very distinguished scientists who actually contributed to the development of quantum theory. Some of them also challenged the theory, and it led to many debates. And in these few lectures, I will acquaint you with the periphery of this topic. It's a deep subject, and it will take a long time to learn it. What I hope to do is give you at least some sort of a introduction so that you can get into the subject and then learn on your own. So what I'm aiming at in these few lectures is to give you an introduction so that you can break into the topic of quantum entanglement and quantum computation. So let me remind you of how the quantum theory itself developed, and right from its beginnings, it was I believe on December 14th, 1899, that at a conference Planck proposed that the black body radiation formula can be accounted for by thinking of the radiation as quantized. And he was not happy with it. It was like doing curve fitting. You adjust some parameters, and then you find that for a certain value of the parameter, you get the best curve. And the black body radiation curve, the intensity versus wavelength curve, could be accounted for by doing this kind of parametrization. And Planck had to think of radiation as quantized. He argued against it. He didn't think that it was a valid theory of nature. He said that it was a purely formal assumption, and it was an act of desperation. So he himself argued against it. And then only when Einstein used that model, used that idea to explain the photoelectric effect, for which Einstein got the Nobel Prize, this was in 1905, and Planck sort of came to terms with his model even after that, I believe in 1908 or something like that. So in that sense, quantum theory owes its origins to Einstein in 1905 and not to Planck in 1900, as some people suggest, and I think there is certainly a case for this. But then we shouldn't forget that the quantum of radiation acquired its meaning only when you take into consideration its statistical interpretation in terms of the Bose-Einstein statistics that the radiation field follows. And it is for this reason that the Planck's constant has got its significance, not just due to Planck but also due to Einstein and subsequently S. N. Bose, which is why it should perhaps be called as a Planck-Einstein-Bose constant rather than just as Planck constant, but that's just a matter of historical records. So, although Einstein contributed to the understanding of quantization of radiation, he was very uncomfortable with the statistical nature of quantum theory. You have all certainly taken courses in quantum mechanics earlier, you are familiar with the uncertainty principle, and whenever you talk about uncertainty, you think about a game of dice and you don't know how it is going to play out. So, Einstein's objection to quantum theory was that God does not play dice. It doesn't mean that Einstein believed in the idea of God. Okay, this was his way of putting across an important objection to the statistical interpretation of quantum theory. Okay, so this is not to be taken as evidence that Einstein believed in God or anything like that. There is no suggestion that he did, but this was a way of communicating his concern about the uncertainty which is intrinsic to quantum theory, and he did not believe that the laws of nature would require this kind of statistical interpretation. But then there were major debates between Einstein and Bohr, and every debate was won by Niels Bohr. And he would then tell him, it's not your business to tell God what to do. So these are great debates, some of the greatest debates in the history of physics or history of science. And the debate can be sort of put forth in many ways. But one thing that the statistical description leads you to is the idea of superposition. We discussed it in the context of the Young's double slit experiment, whether you do it with photons or with electrons. And then when you do this experiment, even with a single photon in the apparatus or even with a single electron in the apparatus, you still get those fringes when both the alternatives are accessible to the system. And it is important that both the alternatives are accessible. If one of these is closed, then you do not get that interference. And therefore, the conclusion that you are led to is a very stunning and shocking one. It means that the particle could go from both slit 1 and slit 2, not one or the other, which is our classical intuitive idea. And the same idea sort of propagates in all phenomena. So this was an experiment which was devised by Schrödinger himself to express this very stunning and counterintuitive consequence of quantum mechanics, that if you have an excited nucleus, then if it is in an excited bound state, then it's probably going to decay, and there is a certain decay probability, there is a certain lifetime, and at any given instant of time you do not know if it is decayed or not. And you can think of an experiment in which it would decay and then a particle comes out, and that particle starts a chain of reactions, a chain of events which cascade, and then this hammer falls on a bottle having poison, and then that poison would kill the cat. But you do not know when this is going to happen, and at any instant of time the nucleus is in a state which may have decayed or not. which essentially leads you to the conclusion that the cat may be dead or alive. And if you want to describe the state of the cat, then you can have to say that, okay, just like this electron or photon which could have gone to either slit 1 or slit 2, and it is a superposition of the two, the cat is in a state of being dead and alive. All right. So this is something which would bother anybody. I think every human being will like to be in this state, no matter what his age is. At least toward the end of his life, he will like to have at least half a chance of being alive. So this is a very counterintuitive idea, and it is some sort of a signature of quantum mechanics, just like the uncertainty principle. And to describe this state, Schrödinger himself coined the term, which in German reads whatever it does, the way it is spelled with V. I cannot, I do not want to venture pronouncing it, but in English it's called as entanglement. Okay, so that's what entanglement is about, that it is in an entangled state. And these are then the consequences of the uncertainty principle, that the dog doesn't bite and bark at the same time, right? And this is a very accurate quantitative statement. It is expressed as an inequality, and the inequality is this: if you take the square roots, then it is this, right? Delta Q delta P greater than or equal to h cross by 2, and see how the delta Q and delta P are defined. They are defined with references to these expectation values of the operators, right? And you have to define the Hilbert space and expectation value. What is the expectation value of the square of an operator? And we have discussed this in our earlier discussions on introduction to quantum mechanics in the previous lectures. So I am not going to go through that, but I do want to remind you of these ideas, because this is a rigorously mathematical expression. It's not something that you can just generate out of your imagination without taking recourse to how delta Q is defined. It is defined as the difference between Q minus the expectation value of the operator Q. So this whole algebra of the Hilbert space formalism, that physical states are represented by vectors in a Hilbert space, dynamical variables as operators, and how the linear algebra is used to extract information. What is the meaning of an expectation value? How does it connect with an average value? So all this mathematical framework. So quantum theory is essentially a set of these mathematical rules which tell you how to get these ideas, and then at the end you have a mechanism through Bohr's correspondence principle and so on to connect it to your observation. So that's what this theory is about. Now, this is the most famous picture in the world, I would say, and this has anybody who was anybody is in this picture. May you name it: Langmuir, Planck, Madame Curie, Lorentz, Einstein. My goodness, this is, even to have a glimpse of any one of them, most of us would go for miles just to see them, and then all of them were sitting at one place. What an awesome moment this was. And this was at the Solvay conference in 1927. And this is where the great debates between Einstein and Bohr took place. So Einstein certainly developed quantum theory. He provided the interpretation of the photoelectric effect, which was one of the major contributions to the origins of quantum theory. But then he also raised many objections to quantum theory. His objections were with regard to the uncertainty principle and the statistical nature, this need to use averages in quantum mechanics to describe the laws of nature. And this is where the Bohr-Einstein debates took place. This is a very exciting story. Sometimes Bohr ended up showing the mistake or the fallacy in Einstein's argument by using Einstein's theory, including the theory of relativity. So it's really very romantic story, which I'm sure some of you would like to read in some details. So Einstein was an amazing genius. Means it's this picture which at the bottom, I really like this picture. It says that everything starts with one super smart dude, which is Albert Einstein. And yes, everything really does. Means it's quantum mechanics, as we have seen. The theory of relativity starts with Einstein, right? Lasers start with Einstein. You are familiar with the Einstein A and B coefficients, right? And quantum computing is based on the idea of entanglement, which got so much attention also because of Einstein's work, because of not because how he explained entanglement, but also because how he made everybody else explain it by raising very deep questions. So Einstein, I think one of the mysteries is that he got only one Nobel Prize. He could have got another one for the special theory, and a third for the general theory, another one for lasers, and one for the EPR paradox and for raising these questions. So I think he was good for easily half a dozen Nobel Prizes. So here is a paradox, that you think of a certain quantity which decays, it bursts, all right, like a photon can decay into an electron-positron pair, all right. And then with conservation of momentum, the electron would go one way, the positron would go the other way, right? And let us come to terms with the fact that yes, the uncertainty principle that delta x delta p must be greater than or equal to h cross over 2 holds, and then it holds for the electron and it also holds for the positron. So there is an uncertainty principle delta x delta p for the electron and a similar relation for the positron. So let us accept this, but then from conservation laws, if you take where the explosion took place as the origin of the x-axis, then you can say that the electron would be this much distance on my right and the positron would be the same distance on my left. And from conservation of momentum, you can also say that the momentum of the electron would be so much and the momentum of the positron and electron you can get from the conservation this thing, right. So it would be the opposite, the P minus would be opposite of P plus. So that would be your logical, intuitive, classical conclusion, although you have accepted the uncertainty principle. Now, you do know that these are two separate particles, and therefore the position of the electron and the position of the positron, you do not have any sense of entanglement or anything like that. So you do not expect any uncertainty between the position of electron and the momentum of the positron, right. These are not canonically conjugate in the classical sense. So you do not expect any uncertainty in those. So you think that okay, you can get these details about the position of the electron and the momentum of the positron, or the position of the positron and the momentum of the electron. You can get this information independently without worrying about the uncertainty principle. And it is, in some sense, you can interpret this as the fact that these two measurements are compatible with each other. They are simultaneous compatible measurements. They will be represented by compatible operators or commuting operators, right. So the corresponding operators would commute. So here you are, and this would be your expectation. You would think that, okay, this is consistent with the uncertainty principle, okay, but it leads you to a paradox, as you will see in the next slide, that if you think of entanglement, then you will have to think of, some way in which information is shared between these two particles instantly, no matter how far they are, okay, if this common sense expectation is to break down. And quantum theory claims that it should break down. And this is something which is disturbing. So, this was Einstein's concern. So, Einstein suggested, his speculation was that there is some information which is there which has not been accessed, which brings about the sharing of this information between these two particles. If they still express, if they still exhibit quantum behavior, quantum entanglement, then it means that quantum theory is not correct, or at the least it is not complete, that there is something missing in it. Okay, this was Einstein's conjecture, that there is some sort of a void in it. And there are then these two arguments in favor of quantum theory being an intrinsically statistical theory, and one that, okay, it gives you statistical nature because some information is missing. So, these are the two alternative views represented by Bohr's position on one side and Einstein's position on one side. And it is not just a matter of conjecture, one has to at some point come up with a resolution of this question, that what exactly is going on. And Einstein's position, and this is reflected, this was the contention of the famous paper which is due to Einstein-Podolsky and Rosen, and it is called as the EPR Paradox. And it had to do with measurements of position and momentum. And the question was that, okay, what exactly is meant by reality? Do position and momentum, do they have a specific significance that you can consider as describing their reality? With quantum theory argues that, okay, measurement of one leads to, missing out on the information about the other. The parameter which is being measured, you get an exact value, it collapses into an eigenstate of that measurement. But then you lose complete information about the canonically conjugate property. Okay. So, if you do not make a measurement, can I then talk about the system having position and momentum accurately without any uncertainties? And this issue is dramatized in this famous question attributed to Einstein, that is the moon there if nobody is looking at it? I do not carry out the measurement, but then do I believe that it is there? So, I know that there is a certain position of an object, and if only I measured it, would it destroy information about the canonically conjugate property. But if I choose not to measure it, can I then talk about the two quantities as a subject of reality which the object has? So, this has a bearing on the interpretation of what is reality. And if this reality requires you to lose information about a particle which is here because they were entangled at some earlier instant of time, and then anything that happens to one particle disturbs information about the other, so that you can resolve the EPR paradox, all right. Then it requires information to be shared between these two particles when they are far apart, and they could be at the ends of my two hands or across the boundary of this campus on this side and on the other, and they could even be like light years and billions of light years apart from each other. But then this information will have to be shared instantly, and that's something which we know from relativity, that there are limits. There is a speed limit, and unlike the speed limits that you can violate in traffic, these are not breakable. Okay, the cop here is nature. Okay, and nature ensures that these limits are not broken. So either the description of reality given by the wave function is not complete, this is one alternative, or else the two quantities, position and momentum, do not have simultaneous reality. That is the kind of inference that you are led to. And Einstein's conclusion was that something is missing in quantum mechanics, and whatever is missing, if it is put back, if we do not know what is missing, but if somebody, maybe one of you, figures out what is missing, puts it back in quantum theory, it will restore causality in quantum theory and remove this. But what it requires, so Einstein's concern was that how can there be this communication? This is what he called a spooky action at a distance. Okay, there is something spooky about it, and I don't think there is any better word for it. So the EPR conclusion, Albert Einstein, Nathan Podolsky and Boris Rosen, the EPR conclusion was that quantum theory is not complete. See, statistics is something which we have to admit in many situations, including classical situations. So this was the question that Einstein, Podolsky and Rosen raised, that can quantum mechanical description of physical reality be considered complete, and this was their paper in 1935, right? And then it took a long time, means this question was there, people were aware of this, there were of course debates on this, Bohr also wrote a paper on this paper, and nonetheless quantum theory had developed. People knew how to do perturbation theory, how to get eigenvalues, okay, how to calculate cross sections, if there were collisions, so the collision dynamics. Dirac came with relativistic quantum mechanics. So a lot of progress was taking place, and everybody was busy using quantum theory. It was something like, okay, don't worry too much about it, just shut up and do the calculations. Okay, calculate the matrix elements and figure out how to do the numerical integration and so on. So that was the focus, and it took like almost 3 decades. In 1964, John Bell wrote a paper on the EPR paradox, and in this paper Bell came up with a mathematical inequality, okay, which sorts of gives you some way of checking which kind of argument is likely to be correct, okay. And this was a marvelous paper by John Bell. It took 30 years after Einstein, and it addressed this question that, okay, is there a spooky action at a distance, and can we carry out some experimental tests so that we can figure out whether it is because of any missing information as Einstein had suspected, or is it because of an intrinsic law of nature which exists by its own right, and entanglement then becomes the signature of the law of nature, and so which was Bohr's position. So Bell came up with some mathematical inequalities, and we have seen that the position and the momentum operators of the electron and positron, they do commute with each other, as one would suspect. And if they did commute, then you can define these difference and sum operators for difference between the positions and the sum of the two momenta. And then you are led to a paradox, because the relation that you land up with is that the position and momentum operators do commute with each other, which is completely in contradiction to the uncertainty principle. So this is the EPR paradox, and this needs a resolution which becomes possible through the arguments which John Bell came up with, how to resolve this paradox. So the EPR position was that quantum mechanics is incomplete, there is something further in it and that information is missing, and that is something that Einstein, Podolsky and Rosen wrote in that paper. But then Bell's inequalities, which we will be introducing in these few lectures, they provide a test for EPR conclusion. Okay, so this is the sum and substance of the Einstein and Bohr argument, that if entanglement can prevent the simultaneous determination of position and momentum, okay, then what is it that enables this entanglement? There is some medium which is responsible. That medium is the missing information, okay, and that is the reason Einstein concluded that quantum mechanics is incomplete, because that is not spelled out in quantum mechanics anywhere. Bohr's argument was that non-local entanglement is intrinsic to quantum mechanics, there is nothing missing, that is all there is to it, and you have to move on. Okay, this is how the law of nature is composed. This is how you can describe the law of nature. So Bell's inequalities will tell us which argument is correct, and this is the debate between two of the greatest giants who have ever lived on this planet. All right, and now a lot of water has flown under the bridge by now. Entanglement has been tested. Nicholas, again I do not know if it is Gissen or Jessen, he and his group carried out some of the first measurements, and they were able to show quantum correlations over long distances, that these correlations actually are there, and they were detected in experiments. And now more recently, a couple of years ago, Chinese physicists carried out some experiments, and they were able to test entanglement over large distances, and this is very nice in some sense, because it comes as an evidence in favor of quantum theory. It allows us to talk about entanglement, and then it enables the development of quantum computers, and that is going to be a very big thing, and most of you in your generation are going to be using quantum theory computers in some way. So I think it's good to get at least some sort of an introduction to this topic. So this is Bohr's paper, can quantum mechanical description of physical reality be considered complete? And this was a counter argument to Einstein-Podolsky and Rosen paper, and it ends up showing some sort of inconsistency in the EPR argument. So this was the debate which continued in the Physical Review papers, and what Bohr says in this paper is that the argumentation of EPR does not justify their conclusion that quantum mechanical description is incomplete. So this was Bohr's conclusion. But then it took a long time to come up with Bell's inequalities. So this was the great debate which many others also participated in this, but mostly people were busy doing using quantum mechanics and building semiconductors and chips and transistors, and the whole technology based on quantum devices was built, and it was making great progress through transistors and lasers. But then there was this nagging question as to what is the nature of probability in quantum theory. Okay? So Bell was able to formulate this in terms of a mathematical inequality, which is what we will be discussing in these few classes. Bell wrote this paper in 1964, and what the Bell's theorem does is to rule out the idea of local hidden variables, which was the contention of the Einstein-Podolsky-Rosen argument. So that is what the Bell's inequalities are about, and they help us set up experiments which would sort of determine the answer to this huge question which was debated between Bohr and Einstein. So that is what the Bell's inequalities are about. So in this first lecture on this topic, I wanted to give you an overview of the historical context in which this question was raised, the disturbing arguments on both sides of the debate, and it is so confusing that you lose track of what you ought to expect out of common sense, which Voltaire always said is not all that common. So anyhow, so we will stop here for this class, and we will continue from this point in the next. If there are any questions, I can take those. Is it?
So when we are talking about positron and electron coming out from a photon, we never took took in account the momentum and position of the photon in the first place. Then how can we go on in taking in account?
No, we do, because it is the original energy. It is the mass energy equivalence, and the energy and the momentum, whatever the photon had, is going to be found to be shared in the product particles.
But then then the question comes.
Yeah, you can take that into account and add that to one or the other and distribute it between the two particles.
But then the question comes that how did we exactly find the position and momentum both simultaneously of that photon?
It's not a question of how you carry out the measurement. Okay, this is a thought experiment, and you know that if you know the original energy of the photon, all right, which is just the momentum times the speed of light. So you know the momentum, okay, and from the frequency you know the energy as well. And it is this, so you know the original momentum which is available to the products, and at whatever location this disintegration takes place, that would be the zero of the two, and then by sharing the momentum that was available before this happened, you could in principle tell the positions and the momentum of these two product fragments.
But then
So all you need is the initial momentum. This is just like a collision experiment in classical mechanics, that okay, you have a board of caroms, for example, and you've got the striker which strikes it, and you know the original momentum of the striker. Then in principle you can find out the distribution of position and momenta of the other coins, right. So in principle it is possible to get the position and momentum of all the product fragments. And it is this idea which is used, not the experimental detail about how such an experiment could be carried out. That's not the thing, which is why it is called as a Gedanken experiment or a thought experiment. And we are worried about what the conclusions that this thought experiment leads us to. And we know from this thought experiment that the actual phenomenology which is taking place is no different from how a board of caroms, coins on a board of caroms would react to the striker. And in principle, you can find the positions and momenta of the other coins. And if you can, then you have to worry about how would you interpret entanglement. That's the question, not the details of how this experiment is done. But in principle, you can get this information. Yes, any other question? Yeah, just repeat your question.
Can chaos be actually considered like a part of entanglement means?
No. Chaos is a very classical phenomenon. It is deterministic. You can predict when chaos would take place. Okay, this Feigenbaum coefficients and so on can be used to predict when it would happen. And more importantly, it is triggered by these initial conditions and not in this incompatibility of measurements of canonically conjugate variables. So chaos is a very different thing. It has nothing to do with quantum uncertainties. Chaotic behavior is not statistical because you can actually predict what the outcome will be. Okay, you can predict it exactly. So there is no uncertainty, no quantum uncertainty associated with chaos. It is, you can predict it, but the predicted value is so sensitive to the initial condition that it could be either this or this, and that is what makes it chaotic. Whereas in quantum uncertainties, you get information about the position, and you have no idea, any idea at all about what the momentum would be. So it's very different.